moon of the week, and this week it's Saturn's moon Enceladus, which has become the focus of much attention in recent years because of the discoveries made by NASA's Cassini probe. And we're going to just have a look at this moon. So first of all, just some basic facts about Enceladus. It's the sixth largest moon of Saturn. It orbits between Tethys and Dione. You can see there. That's where it is in relation to the other moons. So it's one of the inner moons of Saturn. It's got a diameter of more or less 500 kilometers. It's not quite spherical, so that the pole-to-pole diameter and the equatorial diameter do actually vary, although not by much, but it's not an exact sphere. It's got a surface temperature of minus 198 degrees Celsius, which makes it incredibly cold, obviously. And it was discovered in 1789 by William Herschel. It has a very high albedo of 0.81. The albedo is the amount of light that is reflected off it by the sun. So it is incredibly bright, and until the space age, it was never really clear why this moon was so incredibly bright, because it reflects nearly all of the sun's light. It orbits actually in one of Saturn's rings, the densest and the most diffuse part of Saturn's E ring. And you can see the E ring there. The rings of Saturn are given letters, and that's the E ring. And it was imaged first close up by Voyagers 1 and 2. This is a Voyager 2 image of Enceladus. Now, after the Voyagers, scientists were left with two questions, really. The first thing that you see when you look at Enceladus, you'll notice that it has a varied terrain with some cratered areas, but the rest of it is very, very smooth. And the fact that it's very smooth indicates that it's a very young landscape. So the question they asked, well, why are there these two types of terrain? Why is there a cratered area and a perfectly smooth area? How did that happen? And also they were intrigued by the fact that Enceladus does orbit within the densest and the most diffuse part of the E ring. And these were questions that astronomers really wanted to know the answers to. And it had to await the arrival at Saturn of the famous and much missed Cassini probe, because Cassini discovered that in fact Enceladus is venting large amounts of water and water vapor and ice from an area near the south pole of the moon. And this is a false color image, but you can see there that there's a lot of activity going on there. And these plumes, Cassini discovered, were found to originate from fissures in the South Polar region, which were nicknamed tiger stripes. And there you can see emissions coming from those tiger stripes towards the South Pole of Enceladus. And that's where they are in the yellow box. Those are the tiger stripes, sort of parallel fissures towards the South Pole. And this was a complete revelation that nobody really expected to see this activity on this moon. Here's a close-up of those tiger stripes, and you can there's actually one closer, and this is a Cassini image, and this is, I think, really dramatic image of one of those tiger stripes. And obviously, this is something that was not well understood. Here's a lovely image of a backlit Enceladus, where you can see quite clearly that or those plumes of material emanating from the tiger stripes. And here's a close-up that Cassini did. And, that material is very bright, indicating a lot of ice in it that's reflecting sunlight incredibly. And this, of course, explains the albedo of Enceladus, because some of that material falls back onto the surface to coat the whole moon in ice. But some other quantity of that ejected material escapes into space, where it actually forms the E-ring. So what Cassini discovered was that the whole of the E-ring consists of material that has been ejected from this little moon Enceladus. And there's a lovely image showing that quite clearly with Enceladus in the middle and that arc of material in the E-ring. So this was the first time that a moon near Saturn certainly has ever been seen to act in this way. It's a really, really active moon. And here's an artist's impression of what it might look like if you were actually there. I think that's a lovely painting, and it really does give the impression of that incredible activity going on at the surface. Here's a time lapse of Enceladus when Cassini was approaching it, and you can't miss what's happening there. And here's another one receding from Enceladus with those plumes really brightly illuminated, reflecting a lot of light. So here's what astronomers think is happening. As Enceladus has an icy crust, which isn't shown to scale here, but it's thought to be about 5 kilometers thick. And beneath that ice, there is thought to be a global ocean. So Enceladus is in fact a water world, as are many other or several other moons in the solar system, beneath the global ocean. And nobody knows how deep that global ocean is, but Enceladus is thought to have a rocky core. And that material from the ocean is spurting out of the tiger stripes towards the South Pole. Now, the exact mechanism for that is shown here, that you have tidal heating coming from below, and the water rises through cracks and becomes partially melted below the surface, below the crust, and eventually expands and it vents to the surface, and the melted ice drains back into the ocean from those sort of reservoirs. Now, what happened with Cassini is that the mission managers and the engineers came up with an amazing adaptation of Cassini to enable it to fly through one of those plumes to actually analyze what was in the plumes. And it did this a few times. The first time was on March the 12th, 2008. Cassini dipped low to fly right through one of those plumes and sampled it and analyzed what was in the plumes. And there were lots of surprises in the plumes, because in the plumes there was a lot of water, which is being ejected at about 300 kilograms per second from the tiger stripes. There was crystalline ice. Ice on the Earth doesn't form these types of crystals that we find on Enceladus. There's methane, there's oxygen and nitrogen bearing organics, carbon dioxide, molecular hydrogen. So this is a real sort of potpourri of chemicals that are being ejected from the tiger stripes. And there are also rock fragments in which they found silicon dioxide. But some of those elements, if you like, some of those chemicals had been in contact with rock. So they definitely had come up through a liquid environment and ejected into space. And this is, another good reason for believing that there is a global moon beneath that icy crust of Enceladus. And here it is in a little more detail. Astronomers believe, or planetary scientists believe, that on the ocean floor there might be things that are analogous to the black smokers along the mid-Atlantic ridge on Earth, this geothermal activity. I'm sure you've all seen videos of the black smokers. And on Enceladus, because of the icicles, there will be white smokers. And there you have, as I was talking about, water-rock reactions, which they found in the plume, the particles they found in the plume, the hydrothermal vents leading to the surface jets. So just to summarize all that, Enceladus is an active world with its interior heated by Saturn's gravity, so-called tidal heating. It actually has the purest water ice surface of any body in the solar system, and of course that's constantly being replenished, which explains why the surface is so young and why there are so few craters, because the surface is constantly being resurfaced, if you like, with all of that material falling from the plumes. It has a global underground ocean, and the chemicals and the water vapor and the ice and everything else and the gas actually creates Saturn's E-ring as Enceladus moves round in its orbit around Saturn. And its ocean floor may be home to geothermal features like the black smokers along the mid-Atlantic ridge on Earth. And of course, all of this makes Enceladus a prime candidate for the possible existence of life on this little moon orbiting Saturn. So there you are. That's the moon of the week. Hello, I'm Andy from Space Oddities. Next to black holes, neutron stars are probably the most bizarre objects in the universe. First predicted in 1934 by astronomers Walter Baade and Fritz Zwicky, it was not until 1967 that they were first actually observed by Jocelyn Bell, now Dame Jocelyn Bell Burnell, then a research student at the University of Cambridge. In these Weird Wonders videos, we're going to enter the weird, wonderful world of neutron stars, where matter, magnetism and gravity behave in ways we can scarcely comprehend. In this first episode of the series, I'll be looking at how neutron stars form. Go out under a starry sky in winter or early spring, and you cannot fail to notice the constellation of Orion, one of the most recognisable in the heavens. At Orion's left shoulder there is a bright star with an obvious orange colour. This is Betelgeuse, a red supergiant star some 600 light-years away. Betelgeuse is a truly gigantic star, shown here compared in size to some other giant stars and our Sun, which as you can see is tiny by comparison. Betelgeuse is so vast in size that, despite its distance, astronomers have been able to capture an image of its surface, which is not possible with more than just a few stars. Most stars, even in the largest telescopes, appear as mere points of light. The red giant phase of a star occurs when it nears the end of its life, starts to run out of hydrogen, and puffs up into something monstrous and bloated. This is in fact the fate of our Sun. In 4 or 5 billion years' time, the Sun will be nearing the end of its life and will have expanded to become a red giant star, swallowing Mercury, Venus and very possibly the Earth as well. This picture shows what the Sun may look like from the surface of the Earth when our star becomes a red giant. After millions of years as a red giant, radiation pressure from the core of the Sun will cease and our star will shrink to become a slowly cooling white dwarf star, finally ending its life a cold, dark cinder. But what of stars larger than the Sun? What happens to them? Stars with more than about 8 times the mass of the Sun do not become white dwarfs. Instead, they end the red giant stage of their lives by blowing themselves apart in what's called a Type II supernova explosion, a detonation of such unimaginable magnitude that in just a few seconds the dying star may release more energy than our Sun will emit during its entire 10 billion year life. In this type of supernova, the star blows away its outer layers, leaving just the core of the star behind. Immediately after the supernova explosion, there is no longer any outward radiation pressure from the core of the star. Consequently, in the sudden absence of any resistance, gravity is able to suddenly and violently compress the core, reducing its size from thousands of miles in diameter to just a mere handful of miles across. This process may happen within a few seconds. The atoms in the core are squeezed closer and closer together, so much so that electrons orbiting the atoms are unable to sustain their orbits and crash inwards to the atomic nucleus, combining with the protons to form neutrons as a bizarre ultra-dense element called neutronium. A neutron star is born, which consists largely of neutronium. It possesses between 1 and 3 times the mass of the Sun, packed into a sphere perhaps just 10 miles across. You may be familiar with the periodic table of elements, where each element has an atomic number representing the number of protons present in its nucleus. Hydrogen, for example, is atomic number 1 as it has just 1 proton. Neutronium is numbered 0 in the periodic table because it does not have any protons. They have all been converted to neutrons. At this point, gravity cannot compress the new neutron star any further, as something called neutron degeneracy pressure pushes back against gravity, preventing the neutron star from shrinking further under gravity's relentless assault. The neutron star is now in finely balanced equilibrium. However, if the star was originally 5 times or more the mass of the Sun, not even neutron degeneracy pressure can exert sufficient force to stop collapse of the core altogether. Gravity wins the battle by compressing the core to a mere point, and a black hole is born. Therefore, whether the result of a supernova explosion is a neutron star or a black hole depends purely on the mass of the star. Neutron stars are bizarre objects indeed. Here is one shown for size comparison with Manhattan. Because up to 3 times the mass of the Sun is packed inside this small sphere, its density is almost incomprehensible. 1 teaspoonful of neutronium would weigh 4 billion tons. Because of its huge mass packed into a small area, the gravitational field of a neutron star is perhaps 1,000 billion times stronger than the Earth's. This intense gravity means nothing taller than a millimetre or so can exist on the surface of a neutron star. Anything taller would be immediately crushed by gravity. A neutron star is therefore a perfect sphere. Astronomers sometimes observe violent radiation outbursts on neutron stars which are thought to be starquakes, where the surface might slip by a couple of millimetres. This is enough to generate huge amounts of energy. The incredible gravity also means that if you were to drop a ball from a height of 1 metre onto the surface of an average 12-kilometre diameter neutron star, by the time the ball hits the surface it will be travelling at 1.4 million metres per second or 3.1 million miles per hour. And what of the interior of the neutron star? It must be said that astrophysicists are unsure about what exactly a neutron star looks like on the inside. As we cannot crack one open, we have to be guided by the physics alone, which suggests that the interior is made up of extremely exotic materials which do not exist on the Earth and which cannot be reproduced in a laboratory because of the extreme pressures and forces present. Here's a diagram from NASA showing the possible composition of a neutron star, but we cannot test this model through observations. The starquakes I mentioned earlier might give us an idea in the future of what's going on inside a neutron star, but short of travelling to one and making close-up observations, there's no way to investigate what these bizarre beasts in the cosmic zoo are hiding beneath their surfaces. As the closest neutron star is 170 light-years away, or 1020 trillion miles, we won't be travelling to it in the foreseeable future. Well, that's it for the first part in this series of videos about neutron stars. Next time I'll be looking at pulsars, those rapidly rotating neutron stars which fire huge beams of radio energy from their poles like a celestial lighthouse. I do hope you enjoyed this video, and if you have any questions or observations, please don't hesitate to post them in the comments. We hope you can join us, the Space Oddities, on Mondays here on this channel at 8 PM UK time for astronomy news, chat and discussion from our resident panel of experts. We also hope that you'll subscribe to our channel, like our videos and tell all your friends, co-workers and families about us. Well, from me, Andy, until next time, goodbye.
Welcome to Space Oddities, and especially welcome to this short presentation on spectroscopy. When you get astronomers talking, it's very rare that the words spectra, spectroscopy or spectrograph will not appear. This is not a surprise, as spectroscopy is one of the sharpest tools in an astronomer's toolbox when he is looking at the mysteries of the universe. Before we can talk about spectroscopy, we first have to look at light as a whole. The light that we detect with our eyes comes from our nearest star, which is the Sun. The light we see with our eyes travels the 93 million miles from the Sun to the Earth in 8 minutes and 20 seconds. The light arrives to us in little parcels of energy called photons. Now these photons all have varying energy values, and this decides their wavelength. And that's all I'm going to say on photons. If you want to research them more, then you can do at a later date. For now, all we need is that the energy contained in the photon decides its wavelength. Remember that for later. Right, the full range of light is huge, and as I said, the wavelengths vary a lot. Here is the spectrum of all light, and as you can see, it goes from very low energy waves, which are radio waves, all the way up to the high energy waves, which are gamma rays. For today's purpose, we're going to be looking at the visual light. As you can see, the visual light sits on the spectrum, which is known as the electromagnetic spectrum, just above halfway. It covers a very small part of the spectrum. As I said, the photons are little packets of energy, and they vary. And we can see this by using a very simple experiment, an experiment that you've probably did at school. And that is using a source of light and a triangular prism. If you pass the light through one side of the prism, it gets bounced around 2 or 3 times inside the prism due to the angle of the actual facets, and then it reappears the other side of the prism, and you can project it onto a screen. Now as you can see, you will find a lovely rainbow effect, which stretches on one side from red to the other side, which is blue / ultraviolet. This is showing you the different values of energy in each of the photons. We can test this theory by placing the sensor of a thermometer in the red light, and it will read a temperature. If you then move the sensor to the blue or ultraviolet light, you will see that the temperature is actually higher, because the photons at that end of the spectrum are carrying a higher energy, whereas in the red it's a lower energy, hence the lower temperature. By performing this experiment, you are in good company. Isaac Newton himself used to use this system to split the light into its constituent parts. So a quick recap so far. The low energy photons with long wavelengths sit at the red end of the visual light spectrum, whereas the high energy photons sit at the blue end with their shorter wavelengths, and all the wavelengths in between give us the different colours of the rainbow. Also, visual light is only a very small part of the whole of the electromagnetic spectrum, and sits halfway along. So, back to our original questions. First, what is a spectrograph? A spectrograph is an instrument that separates the light from a star or any other light source into its constituent colours or wavelengths. So it's a bit like the prism we mentioned in the experiment earlier, but gives us the spectrum in a far greater detail. Question 2. What is spectroscopy? Stellar spectroscopy is the analysis of the lines in the spectra of stars, and is by far an astronomer's most important tool for investigating the physical nature of stars. So a spectrograph will give us the spectra of a star, but in far greater detail, in the form of little lines. And the study of these lines in the spectrum will tell us a lot about the star and its environment. So what can we see in this extra detail? We can see the radial velocities of stars, that is, motion of the star towards or away from Earth. We can calculate relative masses, orbital periods, and orbit sizes of stars in a binary system. We can measure temperatures, atmospheric densities, and surface gravities of stars. Also deduce magnetic fields and their strengths on stars. We can glean the chemical composition of stars, what atoms are present and in what states they exist. We can also watch the sunspot cycles, or should we call that star spot cycles. In that list I mentioned surface gravities of stars and also magnetic fields and their strengths on stars. Well, I'm not going to go into these because I consider this more advanced spectroscopy, and you have to use methods like the Zeeman effects and the Stark effects, so we'll leave that for another day. So back to these lines in the spectrum that give us all this information. The lines we see in the spectrum appear either dark or very bright. The dark lines are called absorption lines, while the bright lines are called emission lines. For our purposes, and to make it easier for me, I'm just going to talk about the dark lines that we see, the absorption lines. So what are absorption lines, and how do they get there? Well, to explain this, I must rewind the clock on the life cycle of the photon. The photon is first produced in the centre of the Sun, and it spends probably the next 100,000 years trying to escape the Sun. But in the centre of the Sun there is so many high energy particles that it's being buffeted around, ricocheted, ping-ponged all over the place. But eventually, if it's lucky enough, it will reach the outer layers of the Sun. Now in the outer layers of the Sun are all the elements that the Sun is producing, and also the elements that were present in the star's maternal gas cloud that gave birth to it. Remember I said each photon carries an energy level, which in turn determines its wavelength. Different energy levels, different wavelengths. Now the elements in the outer layers of the Sun are in a state we call ionized. This is where, when an element is exposed to high energy levels and heat, the energy levels and the heat will actually start to strip away electrons from the atom. For example, let's have a look at iron atoms. If an iron atom is in an ionized state, it will carry an energy. So again, it will have its own wavelength. Now, the photon, which is running the gauntlet of all these elements in their ionized states, if it happens to meet an ionized iron atom, which has the same wavelength as the photon, then the photon will be absorbed. And all the other ionized iron atoms with the same wavelength will also be absorbing all the photons with the same wavelength. This results in a deficiency of photons at that specific wavelength actually leaving the Sun's surface. This means when we project the spectrum onto a screen, you will see lines where the photons that have been absorbed are missing from the spectrum, and hence you get your absorption lines. And this tells us that iron at that specific ionized state exists in the Sun's outer layers. On this slide you can see the absorption lines for different elements. But we can also take this one step further. Let's get back to our iron atom. If the iron atom is exposed to higher energy levels and larger heat temperatures, then more of its electrons will be stripped. With the loss of each electron, it will exist in a different state. These ionized states of the iron will be betrayed in the spectral line also. They will be producing their own absorption lines. So what is this telling us? Not only is it telling us that iron is existing in the outer layers of the Sun, but also it is existing in several ionized states. We can see this in the spectral lines. So that also means that the outer layers of the Sun are at different temperatures in different areas, so that these ionized iron states can exist. If the Sun's outer layers were all one uniform temperature, we would only see one ionized state of iron. So the temperature varies over the surface. Job's a good un. There is a way we can test this. If we go back to the prism experiment we talked about earlier, but this time between the light source and the prism itself, if we place a test tube full of hydrogen and then pass the light through the test tube, then the prism, and project the spectrum onto a screen, you will actually see in the spectrum definite black lines. This is the spectral fingerprint of hydrogen. These element fingerprints in the spectra of the stars tells us so much about the star and its environment and where it actually came from. But I also mentioned that we can actually detect movement by again looking at the absorption lines in the spectra. We do this by using a method which is the light equivalent of the Doppler shift. Now, the Doppler shift we've all experienced. It's when a emergency vehicle is coming towards you with its siren going. As it moves towards you, the pitch gets higher and higher. But as soon as it passes you, the pitch gets lower and lower. This is because as the vehicle comes towards you, the sound waves are actually compressed, increasing their frequency. But as it passes you, the sound waves become stretched, giving them a lower frequency, so the tone drops. Well, light acts in exactly the same way. If a bright object is moving towards you, the light waves actually get squeezed, increasing their frequency, which means the whole shift is towards the blue. If an object is moving away from us, the light waves actually get stretched, and the spectrum moves towards the red. This is called the red/blue shift, and it tells us which direction an object is moving, away or towards us. So what do I mean about red shift and blue shift? It means that when we look at the absorption lines in the spectra, if an object is moving towards us, the whole of the absorption lines will move towards the blue end of the spectrum. If it is moving away from us, the absorption lines will slip towards the red, and this indicates which direction it is moving in comparison to us. But this can be taken one step further. We can also, using exactly the same technique of the red shift and the blue shift, detect small wobbles in the stars themselves. Also, it will tell us if a star has a companion, and by watching their separate orbits, by using the red and blue shift, we can determine their size, their orbital lengths, and their masses. And all this can be discerned from the red and blue shift of the stars. Sunspots will be betrayed by the effects they have on the surface of the star themselves, and by looking at the elements and the states of ionization they are existing in. Also, spectroscopy can be turned towards nebulae and galaxies, again looking at the interstellar medium between all the stars, telling us how old the galaxy and all the elements that exist within the interstellar medium. And all this just from looking at a few black lines on a spectrum of a star. Well, I hope this makes it a little bit simpler for you if you didn't know anything about spectra. And keep an eye out for more of these jargon busters. Hopefully there'll be a few more on their way. Remember, you will find us on Monday nights at 8 PM UK time. Come and join the panel, and if you have any questions, drop them in the chat and we'll answer what we can. So I hope to see you soon there. Just before you go, just one more amazing wow fact. Now, we all know the universe started with the Big Bang, and not long after the Big Bang, in cosmological times, the universe cooled enough to actually form the first atoms. The first elements formed were hydrogen at 73%, followed by helium at 25%, and a tiny splattering of other elements. This hydrogen produced so early in the universe's history is all the hydrogen it is ever going to have. No more will ever be made. Now, our bodies are made up between 55 and 75% water. Now, water is 2 hydrogen atoms connected to 1 oxygen atom. So just think about it. The atoms that are going to make up your body, some of them are almost as old as the universe itself. Isn't that amazing? It's a bit of a wow factor, that. Anyway, we'll hope to see you Monday nights. Everybody please take care, and I'll speak to you soon. Bye for now.
Here we go. Thanks. Thanks so much. So this will be the first in a series of presentations on moons of the solar system. And, you know, there are over 220 moons around what what you might call normal moons or traditional moons around planets, over 400 around other small bodies, Kuiper Belt, TNOs. So out of the close to 700 moons in the solar system, what an honor that Titan gets to go first. I think that's just incredible.
Well, I tell you what it is, Lou. It's to coincide with that lovely James Webb image of Titan released last week or the week before. So we thought Titan would be a good first place to start.
Titan is a great place to start, and we've known this is a great place for many years. And I'm going to walk you through a little bit of the history of Titan exploration, tell you why it's an interesting moon, tell you why we are spending so much of ESA and NASA tax dollars to explore it. So let's get going. I can.
You have control.
I have control. Okay. There we go. So back in the 1600s, the first notice, the first observations of Titan that were realized were by Christian Huygens, the Dutch astronomer. And of course, you'll recognize that name because that was what we named the Titan probe that went out to Saturn with the Cassini spacecraft. We named it after Christian Huygens. So in this excerpt from his writings, you see Saturn, and you see two stars. You see one in the kind of at the 3 o'clock position and one at the 7 o'clock position. The 3 o'clock position is actually a star, but the one at the 7 o'clock, that was in fact Titan, and he was able to watch that over time, see that it was moving, calculate an orbit, and so he's credited with the discovery of Titan. Then in 1907, with better optics, better telescopes, it was noticed that Saturn has a quality called limb darkening. This is an edge effect that you would see in a body that has an atmosphere. So as you're penetrating down further into the atmosphere, rather than going from deep space to solid surface, you see a gradation of intensities. And this was the first indication that that Titan had an atmosphere. So that alone makes it unique among all other moons of the solar system. Then in the 1940s, Gerard Kuiper, who you will recognize, the Kuiper Airborne Observatory was named after, as well as the Kuiper Belt. He had two big things named after him. I'm still waiting for my first thing, but I know it's coming. And he did some spectroscopic observations of Titan and noticed that there was methane, or as you say in the UK, methane, in the atmosphere. See, I'm getting an error message. Something went wrong. Try reloading the page. Can you see the slide?
We can see the methane slide, yes.
Okay, very good, very good. And we'll continue. So not only does Titan have an atmosphere, now there's methane in the atmosphere. And why is that interesting? For a couple of reasons. It is a biomarker. It can be the result of biological activity, or it can be a resource for microbial, let's say, activity. And also, it shouldn't be there. Methane is very volatile and gets broken apart into its component elements of carbon and hydrogen very easily with ultraviolet radiation. So the fact that it is there on Titan is something that makes Titan even more interesting. So just a few facts about Titan. By the way, this is an image that was taken by the Cassini VIMS system, Visual and Infrared Mapping Spectrometer. This image is not what you would see if you were just kind of flying out there and looked out your window. In this image, we're looking through the very opaque photochemical haze that surrounds Titan down into the surface. So we see surface and lower atmospheric features. And you can do this between methane absorption bands in the near infrared. And I'll be showing you other pictures and talking about that quality. But just kind of a Titan 101 here. Diameter of 5150 kilometers. Surface gravity of 1.35 meters per second squared. Most of the atmosphere is nitrogen, predominantly nitrogen, just like a planet we all know and love, with other hydrocarbons and nitriles. The surface pressure 50% greater than the Earth. And because Titan doesn't have as much gravity, its atmosphere is much more extended than Earth's atmosphere. And then, of course, it has all of these Earth-like features with seasons and rain and clouds and lakes and rivers. And you say, wow, what a great place. But it does all of this at a temperature of 94 Kelvin. For you Fahrenheit friends, it's 290 degrees below 0 Fahrenheit. So all of the fluvial and atmospheric evapotransport mechanisms that go on are not with water. They are with other very interesting hydrocarbons. Just as comparison of Titan to all the other moons of Saturn, clearly the largest moon. Not all the other moons of Saturn, but many of the larger ones. And here's a comparison with just other solar system objects. So you see Earth and Venus on the left. Venus is about 95% the diameter of Earth. Mars is about half the diameter of Earth. And Titan is next and bigger than Mercury. So if Titan was not orbiting Saturn, it would clearly be another planet. But it is orbiting Saturn, so we don't count it. Well, with all of this, these interesting findings, it's no surprise that we've sent a number of missions out to investigate Titan. We sent the Pioneer 11 to Saturn. This is a flyby mission that flew by in '79. Voyagers 1 and 2 flew by in 1980 and '81, again, flyby missions. And then the Cassini spacecraft on its way with gravity assist from Jupiter, orbited Saturn and dropped the Huygens probe into the atmosphere of Titan. Cassini made many, many close encounters with Titan because it's a very important object of interest. And we'll be looking at some of the observations from that in just a moment. So early on, robotic exploration, Pioneer 11 went to the Saturnian system and took some pictures of Titan. This, it turns out, now I guess I'm not sure if my I have something blocking it here, but this is supposed to be the first robotic spacecraft image of Titan. Of course, this is Saturn here in the middle here with its rings and the shadow of the rings on the beautiful cloud tops of Saturn. But on the bottom, if it's still in frame, is a small dot, and that is the dot. That is the figure of Titan.
Wow.
Pioneer 11.
We've come a long way, haven't we, Lou?
Oh, we have, as I'll show you in just a second. This was the best image of Titan taken by Pioneer 11 at a distance of 360,000 kilometers.
Wow. Pioneer
11 had a 2-color camera. And again, what we're seeing here is this is in the visible part of the spectrum. So you're seeing the atmospheric haze that shrouds the entire planet and prevents visible wavelength light from penetrating. Haze, kind of like smog in LA in the summertime, in Los Angeles in the summertime. And this was the best image that Pioneer 11 had, and at the time, the best image that humanity had of Titan.
Didn't learn a lot then.
There was other data taken,
Right.
Spectroscopy of the atmosphere, magnetic field data, and so on, but that was the best visual image. Then in 1977, the 2 Voyager spacecraft were launched on flyby missions to the outer solar system. And over here on the left, we have, I think this is a Voyager 1 image of Titan, much better image. You can see a couple of things here. Of course, the orange-red photochemical haze. By the way, this is produced by the photodissociation of nitrogen nitrogen and carbon in the atmosphere. And the methane and the nitrogen break into these amazing cacophony of chemicals, which makes Titan even more interesting. You see that the top part of the image here of Titan looks darker than the bottom part. And this is not a solar angle effect. This is actually a compositional and particle size effect, because the atmosphere moves wholesale from one hemisphere to the other every Titan year. And Titan year is roughly 29.5 Earth years, just like Saturn, as it is tidally locked to its planet. You can also see on the top here just a little bit, it looks like it's a little bit not quite round at about your 1 o'clock position. And that is the North Polar Hood, which is a region where chemicals build up in the atmosphere in the winter season for that pole. On the right here, you see some models that we've been able to make of the atmosphere of Titan, showing the photochemical haze, the particulates, and the that are produced, the haze layer further down, and then these hydrocarbons and nitriles kind of precipitate down through the atmosphere and act as nucleation sites for other chemicals to glomp onto, and then they fall out onto the surface. Temperature and pressure of the surface is such that methane can evaporate back up and form methane clouds or methane clouds, and so you have a methane cycle here instead of a water cycle that you'd find on Earth. This is just an example of some of the other kinds of data that we got from the Voyager spacecraft. Obviously, this isn't an image. These squiggly lines come from the IRIS, the infrared interferometer spectrometer on Voyager. And this is from the SATAT link on Voyager 1. Very, very close flyby of Titan.
That's quite a complicated cacophony of chemicals there, isn't it?
It is. It's complicated. It's hard to understand for most people. And so at the daily press conferences, when plus or minus 2 weeks of encounter out at Jet Propulsion Laboratory in Pasadena, California, the imaging team got all of the press and all the oohs and ahs, and we'd show a few of these and nobody cared. But there's an amazing amount of information in here. You can see many of the hydrocarbons and nitriles, HCN, hydrogen cyanide, C2H2, acetylene, CH4, methane, and so on, and ethane, C2H6. Lots and lots of these chemicals that are produced by this prebiotic atmosphere that Titan has. And these images, these little squiggly lines turned out to be very important in understanding the birth and evolution of Titan.
Just out of interest, how does that compare at all with what New Horizons found at Pluto?
In some ways, it does. For example, Pluto has a detached haze layer. We haven't shown that quite yet here. That Titan also has. Pluto's chemistry is different. It's colder, if you can imagine being colder than this. Oops, let's cancel that. But it also has many of the chemicals that we see here. Yes, and I think it deserves its planet status just from that alone.
Indeed.
So we move on, and in 1997, 20 years after Voyager, we launched the Cassini spacecraft with its Huygens Titan probe to Titan. And again, this image here is from the VIMS instrument on Cassini, showing the surface features of Titan. And here we start to see some darker regions. These are lakes on Titan. You can see some of the surface as well as some highlighted parts of the surface, which are likely in this image methane clouds in the lower troposphere of Titan. There's the launch of Cassini. Oops. And here's an artist's rendition of what it would have looked like as Cassini approached the Saturnian system. It released the Huygens probe to fly unaided into the atmosphere of Titan using aerobraking and then eventually a parachute, which, as you might imagine, was is very efficient with a very thick atmosphere of Titan to land on the surface.
And just on that point, Lou, somewhere on YouTube, there is a real-time record of Huygens' descent through the atmosphere that you can sit and watch, which is amazing.
Absolutely. And so landing on the surface was amazing. And we got our first glimpses of the surface, which I'll show you in a minute. But for me, who studied the atmosphere of Titan, the progression of Huygens down through the atmosphere, taking measurements of temperature, pressure, composition at each level was even more important and more interesting. So we got a vertical distribution of temperature, pressure, wind speed, composition, and so on at one place and at one time, but through the atmosphere of Titan.
Well, weren't the winds a bit different to what had been predicted? I seem to remember.
They were, and they were able to track the probe using Doppler measurements that were received by Cassini and then sent to Earth. And the upper atmosphere was a little more turbulent than they had predicted. The lower atmosphere not as turbulent, so this is why you go there, right?
I seem to remember that it took longer to descend through the atmosphere than they thought it was going to.
I think so. Yeah. We had just our models from what little we knew from Voyager and from ground base and Earth orbiting observations.
Yeah.
And I'll show you some of those in a few minutes as well.
Okay.
So this is just.
Sorry, I was going to say, and it all worked amazingly. It was a flawless descent.
Not only a flawless descent, but they pinpointed the landing 1.5 billion kilometers away. So in my way of looking at it, the real heroes of this mission are the people who understood the celestial mechanics of how things operate in the solar system and are able to guide this thing miraculously to a pinpoint landing. So the Huygens probe descended. It had a camera a downward-facing camera, and we started to see now through much of the haze, started to see surface features. You can see what we used to call these fluvial channels or flow channels, and I think we were a little coy about calling them rivers at the time, but you can see valleys and mountain ranges and fluvial channels. And then in the lower right, you see a little more magnified image of the surface in black and white here. Clearly, you see the rivers. You can see the darker area on the bottom, that's hydrocarbon lake. And these little puffy things here are methane clouds in the troposphere.
Amazing.
And I remember being at Cornell University when I was working on this problem with Bob Samuelson. Carl Sagan was working on this problem, and a group from Canada, whose names I'm sorry I forget, were working on this problem of methane clouds in the atmosphere of Titan. We're all using the same data from Voyager 1's observations, and Canadian group said there are clearly no methane clouds. Sagan and Thompson said, yes, there are. And Bob and I said, I don't think we know yet. And it turns out there are. So the probe landed on the surface. We knew that the surface was probably had a collection of liquids on it. And we knew that from atmospheric modeling from the Voyager data, also from active radar measurements from Arecibo, where we bounced radar signals off the surface to see what the scattering profile looked like. And so Huygens was designed to not only land on a hard surface, but a mushy surface or in a lake. And it turns out that it landed in something kind of marshy. What you see here are rocks, probably water ice, covered with tholins, these atmospheric prebiotic chemicals, hydrocarbons, and nitriles, and so on that are falling down through the atmosphere. And then you see some smoother areas, which appear to be liquid hydrocarbons on the surface at the landing spot of Huygens.
And some of those pebbles, if you like, are quite rounded, aren't they? As if they've definitely been in some sort of liquid.
There is erosion on the surface, not only from liquid and atmospherics and so on. And they do not appear jagged at all. From the Cassini orbiter, they were able to take radar measurements of the surface. This is a false color image just to show detail. Well, I guess if you're doing radar measurements, you don't have any color, at least in visible part of the spectrum. But this just shows the a collection near the poles of lakes on the surface of Titan.
Are the lakes restricted to the polar areas?
They're not restricted to the polar areas. We see them at all latitudes. So,
right.
This is an interesting experiment that was done. This is called a radio occultation experiment. You can fly the spacecraft behind Titan, send a radio signal through the edge of the atmosphere and kind of pan down through the atmosphere. And then the Earth receives that signal, which is deflected at some angle and its intensity reduced at some proportion. And that observation gives you a quantity called temperature over mean molecular weight in the atmosphere and allows you to make temperature profiles. So the mean molecular weight is very, very close to 28, 2 times 14 nitrogen, diatomic nitrogen. And so we're able to get a temperature profile, at least for that location, showing how the temperature varies with height. And you can see here in this little graph that Titan has a troposphere like the Earth does. It has a tropopause where the temperature turns over and starts increasing with height. And it has a stratosphere.
Fantastic.
I showed you the Voyager's infrared spectrum of the atmosphere. This is the Cassini infrared spectrum. This was taken by an instrument called CEERS, the Composite Infrared Spectrometer, aboard the Cassini orbiter. And so here we have much higher resolution data identifying all kinds of chemicals, and some of them building blocks for life, like hydrogen cyanide. And so we see this atmosphere that is mildly reducing, and it also produces somewhat of a greenhouse effect on Titan. As cold as the surface of Titan is, about 95 Kelvin, there's about, and I'm sorry I forgot to convert this, there's about a 38-degree increase in the surface temperature Fahrenheit from what it would be without an atmosphere. And this is caused by these chemical species that are asymmetrical, absorbing energy and re-emitting it back down to the surface, just like we have on Earth.
And of course, methane is an extremely potent greenhouse gas.
Yes, absolutely, and the primary volatile species in the lower atmosphere of Titan.
Sure.
From all of this, we're able to construct some models of what the internals of Titan might look like. And what I want to point your attention to here is that there is some indication that there may be a global subsurface ocean with liquid water, perhaps mixed with methane or other hydrocarbons. This is not a surprise, because when you fly a spacecraft by Titan, and you measure the degree that its trajectory is modified by the gravity of Titan, it's not that much. And it equates to a bulk density of about 2 grams per cubic centimeter.
Right.
Earth is about 5.5 grams. So Earth is much more rocky. So we know there's a lot of water, either in liquid form or water ice, making up the composition of Titan. This is another image from Cassini showing a region where it appears that there's some cryovolcanism on the surface of Titan. This was suspected for a while, but here we have some observational evidence. Really exciting finding. Three images from the VIMS instrument on Cassini, showing all sides, all surface areas of Titan. Again, you see the darker areas as the lakes. You see the very whitish areas as clouds. You see surface areas as well as some, I guess these are, I think these are cloud regions. I'm not sure, in the polar areas.
Yeah, probably.
I just think this is a lovely image.
Beautiful. Look at that haze.
It's a bit colorized, but you see the red-orange atmosphere of Titan and the detached haze layer that we, as I mentioned, that we see on Pluto as well as Titan. And it turns out that I painted something that looks an awful lot like this about 30 years ago.
Really?
So I wonder if it was, prolific. This is one of my favorite images. Believe it or not, Cassini got this image just at the right time, just at the right angle to have sunlight reflecting off one of the hydrocarbon lakes on Titan and into the image of Cassini. Just remarkable.
Is that reflection actually an image of the sun?
It is sunlight. It is sunlight reflecting off the lake.
Yeah, but that bright spot is are we looking at a direct reflection of the sun? That's amazing.
Oh, well, I don't know if that's, I wouldn't say that is an image, a spatially resolved image of the sun. I think that's a gradation in.
Yes, probably, yes. But it's very bright, isn't it? Amazing.
Titan is an incredible world.
It is.
So this is an interesting place. It has water, liquid water probably, models indicate, below the surface. It has a prebiotic atmosphere. It has lakes and rivers and seasons and winds and, what do you want out of a body in the solar system? And so we're spending some more tax dollars, at least of the American tax dollars, to go take an even closer look. And this is the Dragonfly mission that will launch, I believe, in 1996. I'm sorry, 2026. 2026. I'm dating myself a little here. This is actually an octocopter. It will have 8 propellers, 8 propeller systems that will fly it around through the atmosphere of Titan. Now, of course, we have a drone on the surface of Mars that's flying. Mars atmosphere being about 1% the density of Earth's. That's a tough ordeal. But the atmosphere of Titan, 50% greater surface pressure, no problem. And this drone, therefore, can be somewhat larger, and it's about the size of maybe a small school bus. It's rather large, with a RTG on the back end here, a radioisotopic thermoelectric generator, nuclear power source, and it is going to parachute into the atmosphere of Titan. I'll show you here in a minute. I'll go over some of the parts. It will have various instruments. Of course, it will have visual imagers and spectrometers and instruments to measure the winds and pressures and temperatures and so on at the surface of Titan.
Just one thing occurred to me about that. Are they at all worried that if it lands on the surface, it might actually freeze and get stuck to the surface?
Well, I'll tell you, in order to do that, you'd have to be able to liquefy water a little bit, right? Yeah,
true.
Water. That's not going to happen on the surface of Titan.
Yeah.
No, this probe is being developed by the Johns Hopkins University Applied Physics Laboratory, and believe me, they are taking the cold temperatures and what we know of the composition of the surface into account.
I'm sure they are.
The hope is that not only will they get more information about the solid surface and the atmosphere, but also the liquid surface. I believe there's a mass spectrometer on board that's going to be able to tell us more about the composition of all 3 of those.
Any idea how long they're expecting Dragonfly to last?
Well, let's see. I believe I have to check. I believe the planned mission on the surface is 2 years.
2 years.
Earth years. Earth years.
Earth years, yeah.
But I imagine almost everything that we send up now is far more durable than its planned lifetime.
Sure.
And so it's not unusual. In fact, I think it's almost the rule that we send up missions that that exceed their lifetime, and we ask for extended funding. And we get that. And if you just look at the Voyager missions, you can understand what that's about. Let's see.
It must be so incredibly hard to design a vehicle that's going to work in those low temperatures and work reliably.
I suspect. I was in Barrow, Alaska a number of years ago, and I remember it was hard just to get my my cell phone operating and
Really?
20 and 40 degree below temperatures. Let's see. So 2 years is not a correct number. I think it's more like 2 months.
2 months, right?
Or for the initial planned mission.
Right.
Sorry.
But as you say, it'll, if past experience is anything to go by, especially with the MERs, then it'll probably last a lot longer.
Right. Just a indication of how it plans to get there. Many gravity assists. That means you don't have to have as large a booster, and you can do this more energy efficiently. It will begin aerobraking through the atmosphere of Titan, and then it will open a parachute that will slow it down until it's able to drop its heat shield. And it's actually going to just drop this thing in midair, and its rotors will begin operating, and it will fly itself to its surface. And remember, we're 1.5 billion kilometers away, so we're not using a joystick to do this. So it has it has sensors, and it has intelligence that's going to be able to pick out a suitable landing site. I think in real stream this cannot play. Okay, right. So this was a video of releasing the Dragonfly probe.
Oh yes, you'd have to show your screen for that, unfortunately.
Right, and so it will copter itself down to the surface. Raise its communication antenna. It will be able to receive signals from the Earth over long periods of time. It will send up science packages to tell it what we'd like it to do. And then it will fly off and look for a suitable landing site. And it will actually be able to fly a little bit further. It does this kind of hip-hop motion where it flies beyond that site, looks for other landing sites, comes back to the original site, and then does that same kind of progression again.
Right.
And I think that is it.
Totally autonomously.
Mm-hmm. Totally autonomously. That's right.
Amazing.
Yep, that's it.
Right. Well, thank you so much, Lou, and I hope viewers you've enjoyed that look at that fascinating world Titan. And yes, thanks, Lou. That was absolutely fantastic. So there you are. That's Titan. And as I said, this is the first in a series of Moons of the Week. And what would you, our viewers, like to see in this series? If you've got a moon that you're particularly fond of and you'd like to learn more information about, then pop it in the chat now, and we'll see what we can do. So as for next week's moon, we need to discuss what we're going to tackle next week. But I can guarantee you it'll be interesting. Because
button moon,
yes, okay,
yeah.
Right. Don't give up your day job. And
Steve's got a question in the chat now. I don't know if anybody can help him with that. What happens at the end of mission? Will the power generating device remain on Titan for good? Is there a danger of polluting?
Well, the mission will remain on Titan. It's not coming back. And so its RTG will remain with it, and it should be, it is well contained. I think the prospects for pollution are very slim. You might remember that the Cassini spacecraft also flew to Saturn with an RTG, and it did a number of gravity assists before it got there, and one of the gravity assists was with Earth. And so there were some environmentalists who were very concerned about what happens if it kind of misses its trajectory and hits Earth's atmosphere, and this radioactive material gets in the atmosphere and kills us all. And the truth is that this stuff is packed very tightly. And my understanding is you can put a string of dynamite around these RTGs, this plutonium, and blow it, and you won't see any degradation. So it's the opportunity for pollution on Titan, I think, is very, very low.
I mean, they drop these RTGs out of planes at 50,000 feet, and they survive. So they are designed not to break open.
They're baked into ceramics, actually. So that's part of the process.
That's right.
Welcome to Space Oddities, and especially welcome to this Astronomy Basic. Today I want to talk to you about the Sun and take a glimpse into the heart of our solar system. The Sun, our celestial neighbour and the centre of our solar system, is a remarkable celestial body. It is a star, a massive ball of hot plasma, a state of matter where atoms are stripped of their electrons, creating a hot, electrically charged gas. The Sun is primarily composed of hydrogen and helium that radiates immense amounts of energy, influencing the Earth's climate, shaping our seasons, and providing the essential light for photosynthesis, the process by which plants convert light into food. The Sun's immense gravitational pull holds the planets in our solar system in their orbits. Understanding the Sun and its workings is crucial to comprehending our place in the universe and the delicate balance that sustains life on our planet. Here is some more essential characteristics of our Sun. Mass. The Sun is about 1.3 million times more massive than Earth, and its diameter is about 109 times larger. Basically, what that is saying is the volume of the Sun, you could actually fit 1,300,000 Earths into it. And with it being 109 times larger, it means across the equator of the Sun you can line up 109 Earths. Composition. The Sun is composed primarily of hydrogen, about 72%, and helium, about 26%. Trace amounts of other elements, including oxygen and carbon and iron, also exist. Temperature. The Sun's core is incredibly hot, reaching temperatures of over 15 million degrees Celsius, which is 27 million and 32 degrees Fahrenheit. The intense heat is the source of the Sun's energy. Energy production. The Sun's energy is generated through nuclear fusion reactions, a process in which hydrogen atoms are fused into helium atoms, creating immense amounts of energy. Radiation. The Sun emits a vast amount of energy in the form of electromagnetic radiation, including visible light, ultraviolet light, infrared radiation, and radio waves. Gravity. The Sun's immense gravity holds the solar system together, keeping the planets and other celestial bodies in their respective orbits. So, how does the Sun work? Nuclear fusion, the Sun's power source. At the heart of the Sun lies the source of its incredible energy output, nuclear fusion. This process involves the merging of hydrogen nuclei into helium nuclei. In this process, two hydrogen nuclei, or protons, collide with such a force that they fuse together, forming a helium nucleus, or an alpha particle, and releasing a neutrino and a gamma-ray photon. This process releases a tremendous amount of energy, accounting for the Sun's luminosity. The fusion reaction in the Sun's core is a continuous process, with approximately 620 million metric tons of hydrogen being converted into helium every second, releasing vast amounts of energy in the form of heat and light, which is then transported outwards through the Sun's layers, ultimately reaching the photosphere and escaping into space. Energy transfer. The energy generated in the core travels outward through two main processes, radiation and convection. Radiation involves the emission of electromagnetic waves, while convection involves the movement of hot plasma carrying energy from the core to the surface. The corona. The Sun's outermost layer, the corona, is a highly ionized plasma that extends far beyond the visible surface. It is the source of solar wind, a stream of charged particles that permeates the solar system. Activity cycles. The Sun's activity, including sunspots, solar flares and coronal mass ejections, varies in a cyclical pattern, with an average period of about 11 years. These events are driven by changes in the Sun's magnetic field. Now let's take a look at the composition and structure of the Sun, the solar interior. The Sun's structure is remarkably intricate, encompassing a vast range of layers and phenomena that contribute to its overall functioning. From the core, where nuclear fusion powers the Sun's energy output, to the outermost layers that unleash solar flares and coronal mass ejections, each component plays a crucial role in the Sun's dynamic nature. In the center, we have the core, the Sun's densest and hottest region, where nuclear fusion reactions relentlessly convert hydrogen nuclei into helium nuclei, releasing immense amounts of energy. The Sun's core, located at its center, is the hottest and densest part, reaching temperatures of up to 15 million degrees Celsius. That is followed by the radiative zone. Surrounding the core, the radiative zone acts as a vast heat transfer medium, transporting energy through the Sun's interior by radiation in the form of photons, similar to how heat travels through a pot of hot water. This is then followed by the convection zone, located above the radiative zone. The convection zone carries the movement of hot plasma upwards and cooler plasma downward through convection currents. The Sun's surface. The photosphere is the visible surface of the Sun, the layer that we see when we look at it with the naked eye, where radiant energy escapes into space in the form of light and heat. The photosphere is characterized by a granular texture, with bright granules representing rising hot plasma and dark intergranular lanes representing sinking cool plasma. It is a thin layer, only about 100 kilometers thick, but it is the source of most of the Sun's energy that reaches Earth. The photosphere is a turbulent region with frequent convection cells, which creates the familiar granulation pattern visible on the solar surface. Above the photosphere comes the chromosphere, the solar atmosphere, a thin reddish layer above the photosphere extending up to about 10,000 kilometers. The solar atmosphere consists of several layers extending outwards from the photosphere. The chromosphere is a layer immediately above the photosphere, is a thin reddish layer that becomes visible during total solar eclipses. It is the source of solar prominences, towering structures of hot plasma that can extend vast distances from the Sun's surface. The final layer is the corona, a superheated atmosphere. The corona is the outermost layer of the Sun's atmosphere, a vast extended region of extremely hot plasma that can reach temperatures of millions of degrees Celsius, extending far into the solar system. It is only visible during total solar eclipses, as its brightness is far fainter than that of the photosphere. It is the source of solar flares and coronal mass ejections. The corona is also the source of the solar wind, a continuous stream of charged particles that flows outwards from the Sun and interacts with the Earth's magnetic field, creating auroras and influencing space weather. Let's look how the Sun influences the Earth. The Sun's influence extends far beyond its visible presence in the sky. Climate and weather. The Sun's energy drives Earth's climate and weather systems. It heats the atmosphere, which in turn heats the oceans, driving ocean currents and influencing precipitation patterns. Photosynthesis. Plants rely on sunlight for photosynthesis, the process of converting sunlight into chemical energy. This process is essential for sustaining life on Earth. Space weather. The Sun's activity can affect Earth's atmosphere and magnetic field, disrupting radio communications, affecting satellites, and causing auroras. Solar radiation. The Sun's radiant energy is absorbed by Earth, providing warmth, which helps maintain the Earth's habitable climate. Solar wind. The Sun emits a constant stream of charged particles called the solar wind, which can affect Earth's magnetosphere, influencing communication systems and satellite operations. Coronal holes. These are sources of enhanced solar winds. Areas of low magnetic activity on the Sun's surface allows more of the energetic particles created by the Sun to escape out into the interplanetary medium. Solar flares. Sudden bursts of energy from the Sun, capable of disrupting power grids and radio communication. Coronal mass ejections. Large expulsions of plasma from the Sun's corona, potentially causing geomagnetic storms that can disrupt power grids and high-frequency radio communications. So let's take a closer look at some of these events that happen on the Sun. Sunspots are phenomena on the Sun's photosphere that appear as temporary spots that are darker than the surrounding areas. The surface of the Sun, the photosphere, is about 10,000 degrees Fahrenheit, while the umbra is about 6,300 degrees F. They are regions of reduced surface temperature and are caused by concentrations of magnetic flux that inhibit convection. In other words, they prevent the hot plasma from rising to the surface in that area due to convection. Hence, a lower temperature is seen in that area. Sunspots appear within highly active magnetic regions, usually in pairs of opposite magnetic polarity. Their number varies according to the approximately 11-year sunspot cycle. A typical spot consists of a dark region called the umbra, surrounded by a lighter region known as the penumbra. Individual pairs of sunspots or groups of sunspots may last between anywhere from a few days to a few months, but eventually will decay. Also, sunspots expand and contract as they move across the Sun's surface, with diameters ranging from 16 kilometers, which is 10 miles, to 160,000 kilometers, which is 100,000 miles. Indicating intense magnetic activity, sunspots accompany other active region phenomena such as coronal loops, prominences, and reconnection events. Most solar flares and coronal mass ejections originate in these magnetically active regions around visible sunspot groupings. Solar flares usually take place in active regions, which are regions on the Sun marked by the presence of strong magnetic fields, typically associated with sunspot groups. As these magnetic fields evolve, they can reach a point of instability and release energy in a variety of forms. These include electromagnetic radiation, i.e. X-rays, which are observed as solar flares. Solar flares are large eruptions of electromagnetic radiation from the Sun lasting from minutes to hours. A sudden outburst of electromagnetic energy travels at the speed of light. Therefore, any effect upon the sunlit side of Earth's exposed outer atmosphere occurs at the same time the event is observed. The increased level of X-ray and extreme ultraviolet, also known as EUV, radiation results in ionization in the lower layers of the ionosphere on the sunlit side of the Earth, and this will cause radio interference or even blackouts. Flares occur in active regions and are often, but not always, accompanied by coronal mass ejection, solar particle events, and other solar phenomena. A coronal mass ejection, or a CME, is a significant ejection of magnetic field and accompanying plasma mass from the Sun's corona into the heliosphere. CMEs are often associated with solar flares and other forms of solar activity, but a broadly accepted theoretical understanding of these relationships has not been established. If a CME enters interplanetary space, it is referred to as an interplanetary coronal mass ejection, or ICME. ICMEs are capable of reaching and colliding with Earth's magnetosphere, where they can cause geomagnetic storms, aurora, and in rare cases damage to electrical power grids. The largest recorded geomagnetic perturbation, resulting presumably from a CME, was the solar storm of 1859, also known as the Carrington event. It disabled parts of the newly created United States telegraph network, starting fires and shocking some telegraph operators. Coronal holes appear as dark areas in the solar corona in extreme ultraviolet, which is EUV, and soft X-ray solar images. A coronal hole is a temporary region of relatively cool, less dense plasma in the solar corona, where the Sun's magnetic fields extend into interplanetary space as an open field. Compared to the corona's usual closed magnetic field that arches between regions of opposite magnetic polarity, the open magnetic field of a coronal hole allows solar wind to escape into space at a much quicker rate. This results in decreased temperature and density of plasma at the site of the coronal hole, as well as an increased speed in the average solar wind measured in interplanetary space. If streams of high-speed solar wind from coronal holes encounter the Earth, they can cause major displays of aurora. Near solar minimum, that is when activities such as coronal mass ejections are far less frequent, solar wind streams are the main cause of geomagnetic storms and associated aura. All these events create various energy levels and temperature ranges which stretch all the way across the electromagnetic spectrum. So to be able to view all these events, we need to look at the Sun in different wavelengths. In this image on the left you can see the Sun in visual light, and you can just see the sunspots. On the right is an ultraviolet image, and you can see far more detail and events that are happening on the actual Sun's surface. This slide shows images of the Sun all taken at the same time and at different wavelengths. They range from visual light all the way up to X-rays. You can see every image is different. It is showing us a different layer of the Sun, with all the different activities and the temperatures that are happening within those regions. If you look underneath, you can actually see what is being exposed by each wavelength. The Sun is a dynamic celestial body, constantly exhibiting various phenomena related to its magnetic field and the movement of plasma within its atmosphere. These phenomena, including sunspots, which are dark blemishes on the photosphere that are cooler than the surrounding plasma, solar flares, sudden bursts of intense electromagnetic radiation and high-energy particles, and coronal mass ejections, CMEs, large eruptions of magnetized plasma from the corona that can travel vast distances into the solar system. The Sun's future. Evolution. The Sun is a middle-aged star, having existed for about 4.5 billion years. It will continue to shine for billions of years more, but as it ages, its luminosity will increase and its surface will become more active. Red giant phase. In about 5 billion years, the Sun will enter its red giant phase, expanding to engulf Mercury and Venus. Earth will likely be vaporized, and life as we know it will cease. White dwarf. After the red giant phase, the Sun will collapse into a white dwarf, a small dense star with very high surface temperature. It will slowly cool over time until it fades into darkness. Conclusion. The Sun, our celestial neighbour and the source of life on Earth, is a magnificent celestial object that continues to amaze scientists with its complex structure and dynamic behaviour. Its immense energy sustains life on Earth and shapes the dynamics of our solar system. Its energy powers our planet, shaping our climate and influencing our daily lives. As we continue to study the Sun, we uncover more about its mysteries, gaining a deeper understanding of the universe and our place within it. If you feel inclined to delve deeper into the workings of the Sun, or just to learn a bit more about space weather, I can highly recommend Dr. Tamitha Skov on YouTube. Or, if you just want to follow the space weather or the Sun's activity, here are a few apps that are all free for you to follow. Well, I hope you enjoyed that, and hope you learned something. And I'll see you again next time. Everyone take care. Bye.
Welcome to the Space Oddities series of Astronomy Basics videos. In this video we're going to be asking the question, what is a magnetar? A magnetar is the most magnetic object known in nature, a type of neutron star with an extremely powerful magnetic field. The magnetic field of a magnetar can be up to 100 trillion times stronger than the magnetic field of the Earth. A magnetar at the distance of the Moon could pull the keys from your pocket or wipe the magnetic strip on your credit card. If you approached a magnetar to within 600 miles of its surface, its magnetism would, quite literally, dissolve all the atoms in your body, leaving you as just a cloud of electrons and ions. Magnetars have distinct properties which distinguish them from other astronomical objects. They are a type of neutron star, but with a few differences. They're very dense. A magnetar has a mass about 1.4 times that of the Sun, but it's only about 20 kilometers in diameter. They're very hot. The surface temperature of a magnetar can be up to 100 million degrees Celsius, and magnetars are very fast rotating. A magnetar can rotate once every few seconds. However, although magnetars are very similar to a typical neutron star, a magnetar can emit up to 100 times more energy. So how do magnetars form? Up until very recently, it was believed that magnetars are the result of a red giant star ending its life in a supernova explosion, leaving behind its ultra-dense core. In other words, a magnetar is a neutron star, much the same as others, but with the addition of an incredible magnetic field. However, recent research seems to suggest that in fact magnetars may not result from red giants at all, but from another, rare type of star. The most recent research into the origins of magnetars has focused on a new type of star called a massive magnetic helium star. These stars are a few times more massive than the Sun and are rich in helium. They are also thought to have very strong magnetic fields. In a study published in the journal Science in August 2023, astronomers found that a massive magnetic helium star called HD 45166 is likely to become a magnetar. The star is located about 3,000 light-years away from the Earth in the constellation of Monoceros. The astronomers studied the star using multiple telescopes, including the European Southern Observatory's Very Large Telescope. They found that the star has a mass of about 3.5 solar masses and a surface temperature of about 20,000 degrees Celsius. Astronomers believe that massive magnetic helium stars must be rare, because to date only around 30 magnetars have been discovered in our galaxy. However, as yet astronomers know little about these strange stars and the process whereby they form magnetars, if indeed that's what they do, which is by no means certain at the moment. Far more research is needed to establish why these stars have such strong magnetic fields in the first place. Magnetars and fast radio bursts. Fast radio bursts, or FRBs for short, are bright bursts of radio waves that come from distant galaxies all over the sky, their distribution seemingly random. They typically last for just a few milliseconds and can carry more energy than the Sun puts out in a year. They are incredibly mysterious and their origin is still unknown. However, there is growing evidence that magnetars may be the source of FRBs. There are several lines of evidence that support the link between magnetars and FRBs. First, the timescales of FRBs and magnetar outbursts are similar. Second, the locations of FRBs are consistent with the locations of magnetars. And third, the energy emitted by FRBs is similar to that emitted by magnetar outbursts. In 2020, astronomers detected a bright radio burst from a magnetar called SGR J1935+2154, which is within our own galaxy, the Milky Way. This burst was very similar to an FRB, and it provided strong evidence that magnetars can indeed be the source of FRBs. However, not all astronomers are convinced that magnetars are the only source of FRBs. Some astronomers believe that FRBs could also be caused by other objects, such as neutron stars with weaker magnetic fields or black holes. More research is needed to definitively determine the origin of FRBs. However, the evidence is mounting that magnetars are a likely culprit. Here are some of the key similarities between magnetars and FRBs. Both are extremely energetic, both are short-lived. Both are thought to originate from distant galaxies. Both are thought to be caused by magnetic fields. However, there are also some key differences between magnetars and FRBs. Magnetars are known to exist, while FRBs are still a mystery. Magnetars are thought to be relatively rare, while FRBs may be more common. Magnetars emit a wide range of frequencies, while FRBs are only seen at radio frequencies. The link between magnetars and FRBs is a hot topic of research in astronomy. As more FRBs are discovered and studied, scientists will be able to better understand these mysterious objects and their origins. Well, that brings us to the end of this brief introduction to magnetars, but just to summarise, magnetars are neutron stars with incredibly strong magnetic fields. Their origins are uncertain, but recent studies link them with a new type of star called a massive magnetic helium star. Magnetars may be the source of fast radio bursts, or FRBs, those enigmatic and powerful bursts of radio waves of incredible power seen all over the sky. Much is still unknown about magnetars, but they seem to be very rare animals in the cosmic zoo. Well, we hope you've enjoyed this video about magnetars. Do keep your eyes open for other videos in the Astronomy Basics series from Space Oddities on our YouTube channel. Until the next time, goodbye. This is why I'm calling it Saturn's weirdest moons. Just give me 1 second, and here we go. Okay, hope you can see that. The first one is this moon, Hyperion, which is most bizarre. As you can see, it's got a surface that resembles a sponge, and Cassini flew by this close distance, about 5,000 miles away, and everybody was just amazed at what this moon actually looked like. Just a few details about Hyperion. It's 360 by 266 kilometers. Do forgive me if I slip between miles and kilometers, because I'm in that difficult age, you know. It's designated Saturn 7. In other words, it's the seventh moon from Saturn going outwards. It's actually 1.5 million kilometers away from Saturn. Its composition is mainly water ice with a bit of rock thrown in. And it's got an incredibly low density for a moon of its size. Now, what this means is when meteoroids, if you want to call them that, bits of rock hit it, instead of causing a big impact and a huge crater and flinging material into the space, the density of Hyperion is so low that it just sort of punctures the surface and digs downwards without actually making a huge crater. So as you can see from this image, if you look down the craters, they're cylindrical rather than sort of bowl-shaped. And this is put down to the low density of the material that allows any incoming rock just to go straight in. As I said, Cassini imaged Hyperion 3 times. The first in September 2005 and the last in May 2015. But Cassini's orbit did not allow it to approach Hyperion any more regularly than that. Only 3 times it managed to fly past the moon. There's a photo from another flyby of Hyperion. The bottom of the craters is a very dark reddish material, similar to the material that we find on some of the other moons like Iapetus, and that's why the crater bottoms appear dark. Complex organics are found in this material on some of the other moons, so it's to be assumed it's virtually the same here. And speaking of Iapetus, I mean, Iapetus is a weird body. Iapetus, those of you of a certain age may remember that in the book 2001: A Space Odyssey, it actually took place at Saturn rather than Jupiter in the book. In the film, it was Jupiter, but the special effects team couldn't come up with a realistic method in those days, back in the mid-60s, of representing Saturn's rings. So they moved the location of the final act of the film to Jupiter, but in the book it was Saturn, and Iapetus is featured in the book because Arthur C. Clarke, who wrote the book, being a man of astronomy, he knew exactly what was odd about Iapetus, and what's been known for a very long time is that Iapetus is dark on one hemisphere, very dark, and very bright on the other hemisphere. And what Cassini found when it got there, as you can see in this image, is almost all of the way around the equator, there's this ridge. It looks like two halves of a moon have sort of been welded together, and that's the weld line. So this is certainly extremely odd. I'll talk about the ridge in a moment. So this was a very odd moon with its bright hemisphere and its dark hemisphere. It's 1492 by 1424 kilometers, so nearly spherical. It's designated Saturn 8. It's 3,560,000 odd kilometers from Saturn. Its composition, again, is mainly water ice with some rock thrown in. And that dark material is thought to have originated from outside Iapetus, perhaps from other moons. And the dark color is thought to be due to sublimation, which is a process where a solid turns from a solid straight into gas with no liquid phase. And that material is then further darkened by the action of sunlight. And it's not quite clear yet, I don't think, although I'm sure Lou or Bernard will correct me. I don't think there's any convincing explanation yet for why only one hemisphere is that dark color and the other hemisphere is covered in ice, which is why it's so bright. So that's Iapetus, but the ridge around the equator on Iapetus is amazing. It's 15 kilometers tall, and if you compare that with Everest's 9 kilometers, so it's getting on for twice the height of Everest, that ridge you see before you. It's thought to be formed from the debris of a ring that Iapetus once had that actually collapsed onto the planet, forming this ridge around the equator. Although I don't think that's settled yet, but I think that's the leading theory, that it's the remains of a ring that collapsed onto the surface, onto the equator of Iapetus. This is an amazing image, but this image I absolutely adore, which is a close-up of that ridge. And I did feature this as one of my favorite space images when it was my turn, because this is such a beautiful, haunting image. And you can imagine exploring that amazing terrain. It's just absolutely stunning. So that's Iapetus. Now we move on to a truly weird moon of Saturn, and this is the moon Pan. Now there are two images of it here taken by Cassini from different angles. It's been called the ravioli moon because it looks like a piece of ravioli. How on earth did a moon like this form and get that again a thin ridge right around its equator? It looks like some sort of a UFO. This moon is very small compared to the others. It's only 35 by 25 kilometers. It's designated Saturn XV111, and it's 133,000 kilometers from the planet. Its composition, although it's uncertain, it hasn't been directly measured. It's presumed to be mainly water ice again, with some rock thrown in. And Pan is what we call a shepherd moon of Saturn. And a shepherd moon is one that literally confines one of Saturn's rings and keeps it as a ring so that it doesn't dissipate and spread out. And in this case, what Pan does is to keep the Encke gap, which is a gap between Saturn's rings, free of material. So it's sweeping up material from the Encke gap all the time. And it's this material that it's swept up, which is thought to fall on its surface and form this equatorial ring over time, over a long time. So it's literally, because the moon is acting as a sort of hoover, if you like, it's hoovering up this material which settles on its equator and forms this incredible ridge around it. Now, just so you know where we are, these are Saturn's rings, and you can see towards the right, there's the Encke gap. So we've got several gaps in Saturn's rings. We've got the Huygens gap. We've got the famous Cassini division, which was first seen by Galileo. We've got the Encke gap, and we've got the smaller Keeler gap. And Pan actually patrols, if you like, within the Encke gap, sweeping up any material that has entered it from the rings. And here's an image taken by Cassini of Pan actually in the Encke gap. So that's a beautiful image of that little moon actually in the middle of the Encke gap there, which I think is an amazing image. We move on now to our last moon of this evening, Atlas. Now, Atlas is another moon that similarly has a ridge around it. This, I think, is an amazing image because basically you're seeing a mountain on the top of the moon with this weird ridge around its equator. And Atlas is, getting on for the same size as Pan, 40 by 35 by 18.6 kilometers. It's designated Saturn XV. It's 137,000 kilometers from the planet. Again, it's thought mainly to be water ice. And because for a long time, Atlas was thought to be shepherding the A ring to make it keep its shape, if you like, it's now thought that it isn't actually a shepherd ring of the A ring at all. And latest information indicates that the ring is kept in its within its limits, if you like, by the action of 3 other moons, Prometheus, Janus, and another one I can't remember. So Atlas is not actually a shepherd moon. But in that case, how did it get that? If it's not picking up material like a shepherd moon does, how does it actually get that ridge around its equator? Well, something that Cassini discovered in 2004 was this ring of material that is actually within the orbit of Atlas. And this is the material that Atlas has swept up and has formed that ridge around its equator. That answers the question. So there you are. So they're the tonight's moons, the weirdest moons of Saturn. And I think you'll agree in terms of what they look like. They're certainly extremely weird moons. So there you are.
Yeah, they certainly are. Yeah. And was there ever, when you mentioned the last group, the 3, you said, what was it? You said Prometheus, Epimetheus. Was there ever one Pandora?
Could be Pandora. Yes, it could be. Have to look that up.
Yeah, I could be wrong there. They're just sort of spread. But you were talking about Hyperion. Of course, Hyperion, as well as looking strange, it's got a very strange behaviour as well. It's tumbling totally out of control.
Yes, it is.
There's nothing unified.
No.
Yeah, nothing unified about its the way it rotates, or it's literally tumbling, and you can't predict anything. Yeah. It keeps changing all the time. Yeah, and as you said, it's a very strange sponge-looking looking thing. But also, I mean, as we know, Saturn's got loads of moons or moonlets, and of course, some of the naming's quite novel. I'll just read you this. Saturn has 2 orbital groups of prograde irregular satellites. The individuals in one are given Inuit names such as Sironwak, and in other Gaelic names as Alborix. Each group could be remains of a larger moon destroyed by collision. Apart from Phoebe, Saturn's retrograde irregular satellites have Norse names and include groupings that could each represent fragments of the same captured asteroid. So, they've got so many, with Jupiter and Saturn having so many moons, they're really having to spread the net to find names for all these things. Names for them. And of course, most of them are found by that group of people sat on the Hawaiian mountain, and all they do all day is look for moons, and they're quite successful at it. So, as we said, they need to get a proper job.
Nice work if you can get it, Daz. That's all I want to say.
Yeah, too right.
Bernard or Lou, do you want to add anything about any of those moons?
I'll let Lou start.
Well, the only thing I was thinking is that this chaotic tumbling of Hyperion seems to be a product of its both its irregular shape and its 4-3 resonance with Titan. So these two qualities act together to give it this kind of strange rotation movement.
Yeah. Thanks. Yeah.
With regards to Iapetus, you were wondering about the difference in one side is brighter and the other side is darker. Isn't that related to the trailing side and the leading side, where the leading side just picks up all the dust and everything as it goes through Saturn, as it orbits around Saturn?
I believe that's correct, Bernard.
Right. So,
Steve's just popped in the chat. Steve's just popped in the chat probably a theory about that. It said if you look at the curved horizon of Iapetus on one side of the ridge and trace it across, it doesn't seem to match the circle on the other side of the ridge, suggesting a compression feature. Maybe.
Interesting.
So you've two things pushing together. So
if that's the case, if it is a case of the leading edge and the trailing edge, or the trailing side, is Iapetus tidally locked?
You're the one who did this presentation. You should know. I forgot.
I've forgotten as well. Yeah.
Too many moons around Saturn.
Most moons are, but I don't know about. I don't know about Iapetus in particular.
Yeah, I'll have to ask ChatGPT about that. Okay, so there we are. So those are the moons of the week. Welcome to another in the series of astronomy basics videos from Space Oddities. In this video, we'll be asking the question, what is a galaxy? Just as the Earth's population is clustered into cities, so stars cluster in galaxies. They are the cities of the universe. A galaxy is an immense metropolis of stars numbering millions or billions. There are an estimated 2 trillion galaxies in the universe. Between the galaxies there is just cold, dark, empty space, devoid of stars, stretching for perhaps millions of light years in every direction. Stars in a galaxy, like the one shown here, orbit its centre, held in the eternal grip of gravity. Galaxies themselves may also cluster, as shown here in this NASA image of Stephan's quintet, a galaxy cluster imaged at infrared wavelengths by the James Webb Space Telescope. Gravity draws the galaxies together into complicated dances. As with skaters on a packed ice rink, collisions are inevitable. However, the encounter takes place over millions of years, during which time the galaxies slowly merge to form one single giant galaxy in a series of elegant dances choreographed by gravity. All these images show galaxies at various stages of merging, pulled into twisted, distorted shapes by their mutual gravity. While these might seem like giant cosmic catastrophes, in reality space is so vast and the distances between stars so enormous that collisions between individual stars are extremely rare. Galaxies are so tenuous that galaxy mergers are like clouds passing through one another. It was the great American astronomer Edwin Hubble who, in the 1930s, was the first to attempt a systematic classification of galaxies based on what he observed. His resulting diagram, shown here, is sometimes referred to as the tuning fork. Hubble classified galaxies into 3 main groups: ellipticals, spirals, and barred spirals. We now know that there are other types of galaxy, but the vast majority of galaxies in the universe fall into one of these 3 categories. Today, Hubble's tuning fork diagram still serves us well as a basic categorization of galaxies. So let's talk about one of Hubble's main classification of galaxies, the spiral galaxies. This archetypal classification of galaxy consists of one or more spiral arms of stars sweeping out from the centre like the arms of a Catherine wheel. At the centre of the galaxy is a bright core of stars separated from each other by astronomically small distances, perhaps 10 million stars per cubic parsec, 1 parsec being 3.23 light years. This core of stars forms a sphere-like structure at the centre of the galaxy called the galactic bulge. This means that the galaxy in profile resembles 2 fried eggs stuck back to back. Right at the very centre of most galaxies is a supermassive black hole, which may possess millions or even billions of times the mass of our Sun. There is a direct linear relationship between the mass of the galactic bulge and the mass of the supermassive black hole, but what this relationship signifies is as yet unclear. Most star formation in galaxies occurs in the dusty spiral arms. When we look up into the night sky from a dark location free from light pollution, we see one of those spiral arms of our galaxy arcing overhead as a ghostly cloud, a river of light made up of countless stars. This we call the Milky Way. Now this can be confusing, as our entire galaxy is also called the Milky Way. When we see the Milky Way in the sky, we are looking inwards towards the middle of the galaxy. The actual centre of our galaxy lies in the constellation of Sagittarius. Another of Hubble's classifications is barred spiral galaxies. Barred spirals, as their name suggests, are a type of spiral galaxy where a bar of stars extends either side of the galactic core. The spiral arms emanate from each end of the bar, as you can see in this illustration. 2/3 of all spiral galaxies are barred spirals. Surprisingly, our own Milky Way galaxy is a barred spiral, although this was not discovered until 2005 from observations made with the Spitzer Space Telescope. The bars in barred spiral galaxies form when the orbits of stars in the galaxy's inner disk become unstable and deviate from a circular path. This can happen for a number of reasons, including interactions with other galaxies. When two galaxies merge or even just pass close to each other, the gravitational forces can disrupt the orbits of stars in both galaxies. This can lead to the formation of a bar in one or both galaxies. Disk instability. The disk of a spiral galaxy is constantly rotating. This rotation creates a centrifugal force that pushes stars outward. However, the gravity of the galaxy's central bulge pulls stars inward. If the centrifugal force is not strong enough to balance the gravitational pull, the disk can become unstable and form a bar. Gas accretion. Spiral galaxies are constantly accreting gas from their surroundings. This gas can fall into the galaxy's disk and spiral inward towards the centre. As the gas falls in, it can lose energy and cause the stars in the disk to slow down, and this can lead to the formation of a bar. Once a bar forms in a spiral galaxy, it can grow over time by attracting more and more stars into its orbit. The bar can also drive the formation of new stars in the galaxy's centre. This is because the bar can channel gas and dust towards the centre, where it can collapse and form new stars. Bars play an important role in the evolution of spiral galaxies. They can help to distribute gas and dust throughout the galaxy, and they can also drive the formation of new stars. Bars may also be responsible for the formation of active galactic nuclei, or AGNs, which are regions of intense star formation and black hole activity at the centres of some galaxies. The main features of an elliptical galaxy are an elliptical shape. Elliptical galaxies have a smooth ellipsoidal shape. They can range from being almost perfectly spherical to elongated ovals. Little gas and dust. Elliptical galaxies contain very little gas and dust. This is because most of the gas and dust in these galaxies has already been consumed to form stars. Old stars. Elliptical galaxies are primarily populated by old stars. These stars are typically red and low mass. Random orbits. The stars in elliptical galaxies have random orbits. This means that they do not move in a disk or spiral pattern, as is the case in spiral galaxies. Large size. Elliptical galaxies are typically very large galaxies. Some of the largest galaxies in the universe are elliptical galaxies. Preferential location in galaxy clusters. Elliptical galaxies are more likely to be found in galaxy clusters than in the field. High luminosity. Elliptical galaxies are also typically very luminous galaxies. This means that they emit a lot of light. Central supermassive black holes. Elliptical galaxies are thought to contain a supermassive black hole at their centres. The mass of the black hole is correlated with the mass of the galaxy. It is believed that elliptical galaxies form as the result of collisions between two or more galaxies. In the distant future, perhaps in about 4 billion years, our own galaxy and the Andromeda galaxy will collide, merge and form an elliptical galaxy, their graceful spiral forms completely disappearing over millions of years, consumed and torn apart by gravity's relentless maw. This is why elliptical galaxies contain very old stars. They are remnants from the galaxies which collided. Elliptical galaxies with their paucity of gas are incapable of giving birth to new stars. This is elliptical galaxy M87 in the constellation of Virgo, some 53 million light-years away. Emanating from its centre is a jet of plasma extending for 5,000 light-years. This jet originates from a supermassive black hole at the centre of the galaxy. In 2017, the Event Horizon Telescope managed to image the black hole in an incredible feat of technology and ingenuity. The radio image of the M87 black hole was on front pages around the world and has since become iconic and will no doubt be written into the history books as our first definitive proof that black holes exist, all evidence of such having hitherto been circumstantial. Well, apart from the main Hubble classifications of galaxies, there are other types. Dwarf galaxies usually comprise just a few million stars and are tiny in comparison to other types, hence their name. They are often found orbiting spiral galaxies, such as the 50 or so found around the Milky Way. Ring galaxies are very rare and comprise a ring of stars surrounding a bright central core. It's not known at present how they form. Irregular galaxies are amorphous galaxies having little or no structure. It's possible they may be the results of galactic collisions. Lenticular galaxies are lens-shaped, hence their name. They are midway between a spiral and an elliptical galaxy. There is much we do not know about how galaxies form and evolve. It is one of the most intense areas of astronomical study. The James Webb Space Telescope, looking back to the dawn of the universe, has shown us early galaxies just a few 100 million years after the Big Bang. How galaxies evolve so quickly in such an astronomically short period of time is not well understood, but it is to be hoped that further JWST observations will shed some light on the conundrum. This image shows some of the very early galaxies imaged by the JWST. It is incredible that we are able to look back in time to the infant universe before the formation of the majestic spiral galaxies. Well, we hope you've enjoyed this introduction to galaxies. Just to summarise, galaxies are vast cities of stars. They're categorised using a system developed by Edwin Hubble. They fall into three main categories: spirals, barred spirals and ellipticals. Galaxies can form clusters comprising up to hundreds of galaxies, and all but a few galaxies have supermassive black holes at their centres. Don't forget to check out our other Astronomy Basics videos in the playlist of the same name on the Space Oddities YouTube channel. Until next time, goodbye.